Well, I'm so excited to be here. It's this is a topic that's very near and dear to my heart. It's something that I've been writing papers about now for well, we've been working on this topic for about 5 years, and so I'm really delighted to get the chance to share some of our perspective with you. Just a couple of warnings. One is that I got here at 1:30 or something last night after a very long day of travel. So if I start babbling incoherently, maybe throw some coffee at me or something to get me back on track. But hopefully my adrenaline's going. I think I'm awake. So I think we'll have fun this morning. I get you back to back for the first two. So that's one thing. I also really owe a debt to my amazing collaborators on this topic. So I just wanted to give them a shout out, specifically to Nathaniel Craig, who's a professor at UC Santa Barbara, Xiaochuan Liu, who's a postdoc in San Diego, Dave Sutherland, who's junior faculty in Glasgow, and also Ian Banta, who was Nathaniel's student. He actually didn't participate much in the stuff that's going to be the main topic, but there will be a few things that I'll refer to, and certainly the work we did together informs the way I think about this stuff. And then, so I also am excited because this is the first time I've come to lecture at a school where I'm prepared. So I actually have notes written, I think, for the whole 5 lectures, and I'll post them, hopefully I'll figure that out today, just a PDF of these handwritten notes. But in particular, I have a plan. So I think I know what we're going to do every day. We'll see how the time goes. But I want to emphasize, that this is really for you. And so please interrupt. If my plan goes out the window, that makes me happy because things were so interactive, we couldn't get to everything. You'll have the notes there to refer to, and so I'll be very excited if everything gets derailed. Okay. And just for lack of time, I'm not going to write out what I expect to do in each lecture, but you'll see on the first page that that's at least what I hope to do. And of course, I may skip some stuff if time is running long. Okay, and another thing in the notes that I wanted to mention is I put some references at the end of the notes, both references to a lot of the papers of mine that I'll be drawing from, but also there's some seminal work by Rodrigo, who you'll hear from today also, and Anish Manohar, who you heard from last week, that I referenced there, and a few other things, and then some lecture notes, both of mine, but also from Rodrigo, from Anish, and I forget what else I put there, but maybe things you already are aware of, but some really nice references, good material to go and study. Okay. Good. I think that was, like, there was one other thing I wanted to say before we get into it, but now I'm blanking. Again, no sleep is okay. If it comes back to me, I'll interject. That's what it was. So good. I want to understand a little bit about who you are. So I'm curious how many of you are working on something related to effective field theory. Just raise your hands. Okay, not everybody. Good, about half. And of those of you who are, how many people in the room would say if I say what is SMEFT, that you could give me some kind of answer? Okay, that's really helpful. Okay, so not a lot of people thinking about SMEFT. Perfect. So then today the 2 lectures today I think will be really helpful, and that also will slow me down. I wasn't sure if I should just race through the definitions. It seems like no. It seems like this is going to be new to a lot of you, so that's great. Good. So I want to spend this first lecture really talking about kind of the big picture, okay? What's the big deal? Why did they give me 5 hours of your time to tell you about SMEFT and HEFT? And by the way, I want to warn you that these lectures are going to have essentially zero phenomenology in them, okay? I really want to talk about kind of the big picture and the formalism for understanding, in particular, less what is SMEFT. I think you'll see that it's pretty straightforward to define that. And even it's straightforward to define HEFT, but really I want to spend our time together linking the two descriptions, these two effective field theories for BSM. So, I mean, that's really the point, maybe it's worth writing, is we're really talking about EFT for beyond the standard model, okay? So, the big picture here is that we're now, when the LHC turned on, which was when I was a graduate student, we were all expecting to have a so-called LHC inverse problem. Okay, so this was a hot topic, is that everybody was worried that the LHC would have so many different signatures of new physics that it would be difficult to disentangle what was going on, that we would have trouble understanding what the theory really was, okay? And so this fear of the LHC inverse problem led to tremendous developments in the way we think about LHC searches. So the idea of simplified models in particular, which of course to you probably seems like a completely obvious idea. If you haven't heard of that, that's basically take the standard model and add 1 or 2 new particles at a time and look for those signatures and kind of optimize searches, looking for the signatures of 1 or 2 particles. That was actually a revolutionary idea, surprisingly, because historically what people had done is they had looked for so-called complete theories of new physics, okay, which had lots and lots of particles and lots of complementary signatures. And so this idea of looking at, of sort of targeting signature space, right, building a model as simple as possible to generate some possible signature was really quite a profound change in the way that we approached doing phenomenology. And of course, that then led to all the amazing searches that have been done and are continuing to be done at the LHC looking for new physics. But in the beginning of running a Hadron Collider, you really get a big boost from the fact that you've gone to some new high energy, okay? So you're hoping to make new on-shell states. But as the Hadron Collider runs longer and longer, you kind of transition from an era of discovering new physics directly to discovering new physics indirectly, okay? So of course, we still have a hope that we could find the evidence of direct evidence of new particles at the LHC. There's lots of great work being done in that direction, lots of interesting new signatures being discovered and so on, but really the program is transitioning as we speak to looking for the signs of new physics indirectly, okay? And that's really where the effective field theory techniques that we'll start talking about today are so important for understanding, for providing us with a systematic way of organizing our thinking, okay? So to me at least, you're getting my idiosyncratic take. So, for me, we're going to talk a lot about formalism, and it may seem like you may get the impression that I really just care about this geometry and field space and blah, blah, blah. Actually, I mean, I think all of that stuff is intellectually very interesting, and I've had a blast working on it and learning about it. But the reality is that I'm really in this game to find, signatures of new physics. So oh, I'm writing too high. That's what you asked me not to do. So, to me, this is the question that I wake up in the middle of the night worrying about. I think this is the central question that we all are worried about is, where do human beings have access, potential experimental access to some signature of new physics? And so that's really fundamentally what this is all about, at least again, to me, is we want to look for indirect signatures And to do that, we need some kind of tool, organizing principle, some theoretical structure, okay, to hand to our experimental friends who can then go do the real hard work of actually searching for these things, okay? And let me just say, again, since not everybody here thinks about this stuff, by indirect, what I mean is looking, for example, at distributions or correlations among standard model particles, okay? Not because they're coming from the decay of some heavy particle, but because they're coming from, if you like, some off-shell physics, right? In the sense that I think now you're probably very familiar with from the lectures you got last week, right? There's some new heavy state. We're going to integrate out that new heavy state. That's going to give us some tower of effective operators that are encoding indirectly the fact that there was new physics, right, at some UV scale. Okay, is that a familiar? That part at least is a familiar idea, right? That's kind of the philosophy of applying effective field theory to BSM. Okay, so that idea is I don't need to review, right? The idea that the heavy propagator shrink to points and so on, right? That stuff you did last week. Good. So, something I want to emphasize to you also, because you'll hear a lot of people will talk about SMEFT. Why do we care about SMEFT? What's the benefit of using SMEFT? People will use this phrase, model independent. Okay? And this is a major overselling of what EFT can do for you, okay? And so I like to say model independent is a very strong statement, right? That's saying if I write down the standard model EFT, the SMEFT, and then I'm capturing all possible signatures of new physics that could be there indirectly, okay? That's kind of what people are hinting at when they say that something that SMEFT is model independent. Well, that's really a big overstatement. And one of the main themes of my lectures is going to be to try to help you see what are the assumptions that we're making when we write down the SMEFT, okay? And so you'll see that, okay, it's not model independent completely. Of course, it covers a huge class of UV models, and so that's why it's really useful. I like to be pedantic and say model agnostic instead of model independent. Really just for me, I think that kind of emphasizes that, that we're not talking about something that covers every possible scenario, but instead we're talking about something that covers many, many, many classes of UV models, okay? So something I hope you'll take home with you from these lectures is exactly what kinds of theories we're actually searching for when we use the SMEFT to parameterize the signatures of new physics, okay? And in particular, I want to, because this is a school, when we say it's model independent, okay, there are a few assumptions, and we'll get into this more, but I just want to emphasize that power counting is a UV hypothesis, okay? And the beauty of EFT is that you can talk about everything in the infrared at low energies, okay? I can phrase my assumptions about the UV all in terms of low energy degrees of freedom and properties of the low energy theory. But in particular, this idea of the power counting expansion, okay, of organizing the EFT in terms of more and more effective operators is making an assumption about the ultraviolet, okay? This is, if you like, this is one of the big places where a hypothesis is hiding, okay? And so when people tell you this, okay, you can say, yes, it's quite model independent, but just be careful, you're always making some UV assumptions when you write down the SMEFT, okay? In particular, when you organize the operator expansion in terms of mass dimension, that is capturing the indirect signs of new physics from a certain type of model, as we'll get into, okay? And time. So, good. Any questions about that before we get into a little bit more technical stuff? You have to be more awake than me, so. Okay. So if we're going to talk about effective field theories, again, I hope as you now have a lot of experience from last week in thinking about these ideas, we need to start with what are our building blocks? How do we build the EFT? Okay. And so in particular, we're going to be talking about two versions of the standard model as an effective field theory. Okay. And they're there in the title. So the first one is SMEFT. Okay, so we want to know how to build the EFT. Okay, so in these lectures, the question is, should we work with the Higgs Vev equals 0 or the Higgs Vev non-zero? Okay, this is a simple way of distinguishing between the two approaches to building EFTs for extending the standard model, okay? So if we work with V equals 0, this is what we call the SMEFT, okay? The standard model EFT. And for me at least, you know, this is the thing that if you told me take the standard model and extend it by higher dimension operators, this is what I would naively do. After all, when we construct the standard model itself, we're always writing things down in this SU3 cross SU2 cross U1 language. We use a capital H Higgs field, right? A Higgs doublet that we then use to build the standard model Lagrangian. And only after we've written the Lagrangian in the symmetric phase with the Vev turned off, do we then minimize the potential, right? Find the masses, find the mixings, and so on. And so it really, it seems natural if we're going to extend the standard model by adding operators that we would use the same philosophy, okay? That we would extend it by working with the Vev turned off first and then find a new vacuum. And by the way, when we add these higher dimension operators to the standard model, we shift around where the Vev is. So you need to re-minimize the Higgs potential and so on, because the Higgs potential is now different, okay? So that's the approach that we call SMEFT, and that's the sort of standard tool that's used most in experimental searches these days, if they're using EFT, okay? But there's another approach, which is we could, in principle, set the Vev to be non-zero from the start, okay? And again, you heard a lot about these techniques last week in your lectures on chiral perturbation theory from Anish. But the idea is the same, okay? We have some symmetry breaking. We know what the symmetry breaking coset is, and so we can construct the theory directly in the broken phase, okay? That's what you do for the theory of pions, right? Because we don't have a perturbative description of the symmetry breaking when it comes to QCD, so we just know that there's this symmetry breaking pattern, and then we can write down the theory that respects that symmetry nonlinearly, right? And so we could do the same thing in the standard model. We could work directly with the Vev being non-zero from the start, okay? And this is what most of us now call HEFT, okay? There are various, you may, if you look in the literature, especially from, maybe it's 20 years ago now, I didn't go remind myself of the original literature, but the HEFT is sometimes called the electroweak chiral Lagrangian or something like this, okay? But we're just gonna call this HEFT, okay? The Higgs effective theory, to emphasize that we're building it using the physical Higgs, okay? But really it's just because SMEFT was taken, okay? We need another name, okay? So we wanna know what are the differences in constructing the standard model as an EFT from these 2 points of view, okay? And in particular, as I'll emphasize, we want to understand what I want to bring to this is the question, is this description necessary, okay? Should we, because this is more complicated to work with, right? You saw last week all the technology you need in order to build a model with these nonlinearly realized symmetries, whereas, you know, SMEFT is somewhat straightforward. There are subtleties here too, okay? But nonetheless, this is technically more difficult to deal with. It's also conceptually more difficult for reasons that I'll highlight. And so, so the question is, you know, which of these EFTs should we work with? And in particular, it really comes back to this question, okay, what UV hypothesis are we making? What types of theories of new physics are we interested in probing, okay? What brought me into this subject was the question, okay? I know this is a bit of a mess, it's harder to work with. And again, I'm gonna define all these things carefully for you in a moment, okay? But I know that this is the thing that most people are using, but by not using HEFT, what are we missing, okay? Because clearly we're making a different hypothesis. In this case, it's actually a broader hypothesis, okay? We're capturing a wider class of models of new physics. So if we're too focused on SMEFT, is it possible that we're biasing the way we're doing the experimental program in such a way that maybe we're gonna miss the first signs of new physics, okay? And we're gonna delay progress or even never know that lurking inside the LHC data is some signature of BSM, okay, that we could have found. And so, so to me, I think it's actually a critical question, okay, to tell our colleagues running the experiments that this is enough, or that actually they are going to have to turn to learning and dealing with this description, okay, this more general parameterization. So not exactly. As I'll show you, I mean, these are intimately related. And in fact, what you really do when you do calculations is you formulate the theory this way, okay? But then you actually turn on the VEV, so you're effectively working with this description, okay? But as you'll see, what ends up happening is when you write the EFT as HEFT directly, you're sort of reorganizing the operator expansion, so and allowing for a more general class of possibilities, okay? So but it's really the way in which it reorganizes the operator expansion that makes the comparison between these so tricky and led us to write, you know, at this point, hundreds of pages about this topic, okay? Plus all of the great stuff from others. And so, so that's really gonna be one of the main points of the lectures is gonna be to understand both what are we assuming here, but also how do we map between these two pictures in a way that's self-consistent, okay? Yeah, so and your question is kind of touching on something we'll get to eventually, but I think really more directly, it's really about just this this comparison of these two ways of writing the theory. Okay. Great. Any other questions here? Yes, please. Sorry, yes. So yeah, so it's exactly the same standard model in both cases, right? Here I just use the standard model Lagrangian with the VEV non-zero, and then it's really about the way in which I add the higher dimension operators. Maybe if I write the next thing, I think it'll be clear because I can be much more concrete. Okay, so let me tell you, let me know if this answers your question, and then we can talk more. So basically, what do I mean when I say building the theory these two ways? Okay, so when we want to build an EFT, stop there. What we do is we specify the following three ingredients. Okay, we need to know what are the degrees of freedom. In this case, it's just going to be the standard model fields. We want to know what are the symmetries. Okay, so we're going to, of course, we're going to have Poincare invariance. But then the question is, do we want to impose the SU2 cross U1 as a global symmetry before we gauge it in order to build the Lagrangian, or do we want to work just directly with the U1 of electromagnetism? And then the third thing is we need a power counting prescription. Okay, so we want to know how do we organize our operators as a power counting expansion. So in particular, let's talk about these two cases. So if I have SMEFT with the VEV equals 0, then my degrees of freedom here are capital H plus, of course, the fermions and the gauge bosons of the Standard Model. Maybe this is a good point to mention that in these lectures, I'm really only going to talk about the Higgs sector of the Standard Model, okay, the scalar sector, and I'm going to even make a simplifying assumption in a bit that makes all the formulas much simpler. And so, yeah, so here I'll be specifically talking about the Higgs sector, okay, but of course there's the rest of the Standard Model fields here, okay, that we're just not going to specify, so don't let that confuse you. And again, I'm going to focus only on the Higgs sector, so the symmetries I'll care about are SU2 cross U1. And then the power counting here is organized by mass dimension. Okay, so I just use the canonical dimension of the fields to organize the operator expansion, right? I have more fields and derivatives, that gives me an operator with higher dimension, okay, and so that's higher order in the power counting expansion. Okay, so this is SMEFT, right? V equals 0, and these are the rules I'm going to use to build SMEFT. And we can contrast that against HEFT with V non-zero. So now I have, instead of the complex doublet I have here, okay, here I have the Higgs, the physical Higgs boson, little h, okay? So that's just a singlet scalar, one real degree of freedom. And then I have the Goldstone bosons, okay? They get eaten by the W and the Z, but again, we're going to just work with the scalar part, so we'll work with the Goldstones directly, okay? But you should think of these, of course, as being essentially the longitudinal degrees of freedom of the W and the Z, okay? Especially at high energies when you have Goldstone equivalents and so on. Okay, so these are the degrees of freedom in the scalar sector. Again, of course, plus the rest of the Standard Model. Here, okay, we're only going to enforce that we have U1 E and M, and we have the electroweak symmetry, say EW, is nonlinearly realized. Okay. Again, as I'm assuming, as you're now familiar with from last week, but we'll review this a little bit here in this context. And then, so then there's the question of what's the power counting expansion, and so in a chiral, in like the chiral Lagrangian for pions, right? What we're doing there is a derivative expansion, okay? And so here it's essentially the same thing, but now we can add these singlet scalars, okay? So there's this extra Higgs that we can kind of tack on to everything at no cost, apparently, in this derivative power counting. So you need more. And to be honest, this is not something, so I'm not somebody who goes and does hard calculations using HEFT. This is a place where there's a lot of argument in the literature, okay? People have strong opinions. I honestly don't have such a strong opinion because, as you'll see, I mean, I think that HEFT ultimately is only relevant to a pretty limited class of models that are not covered by SMEFT, okay? So that's gonna be something I'm gonna try to convince you of in these 5 hours. Nonetheless, there's, you know, you are making, again, a UV hypothesis here, okay? And what's important, by the way, if you get into this literature, if you start to worry about actually organizing HEFT as a power counting expansion, you know, people will talk about the interplay of tree level and loop level diagrams. There's something, again, I'm sure you heard last week about naive dimensional analysis. So there's a version of that for HEFT, okay? So there are ways of organizing these things. And maybe we can come back to, if we have time, we can talk about this a bit more once we have more context for understanding what HEFT is really doing for us that SMEFT is not capturing. Yes? Yeah. So SMEFT, we linearly realize SU2 cross U1, right? Is it what? This is before symmetry breaking, right? So this is just like when we construct the Standard Model, right? We write down all possible operators consistent with SU2 cross U1 up to dimension 4, right? And then we minimize the Higgs potential, we break the symmetry. So all we're doing in SMEFT is now we're adding the dimension 5 and 6 and 7 operators and so on. And then we go to the physical vacuum, we break the symmetry. Here, we're working in the broken phase directly. So we're bypassing that first step of writing the symmetric version of the theory. We're just going directly to the broken phase. Good. So this is a very long board. Maybe I'll write it over here. So let's make a simplifying assumption. It's just going to make the formulas easier to read and make the math a bit simpler. And it's really we're going to be able to tell the whole story, okay? So we're going to assume always here, sorry, that's probably assume custodial symmetry okay, which is basically just this is a property of the standard model. If you're not familiar with this idea, this is a very important idea for just understanding the standard model. So we promote SU2 cross U1 in the standard model and maybe I'll add the left and hypercharge labels here. So we promote this to SU2 left cross now SU2 right. Okay, so the U1 of hypercharge is the U1 subgroup of SU2 right, and the point is that if I turn off the gauge coupling for the hypercharge, okay, the G prime we usually call it, and I turn off the mass splittings and the Yukawa couplings, or if you like, I just turn off the Yukawa couplings, then actually there's this bigger global symmetry in the standard model, okay, we call it custodial symmetry, and then we can organize thinking about standard model predictions in terms of breaking of custodial symmetry due to those parameters G prime or the Yukawas. And what's going to be useful for us is that this SU2 cross SU2 structure is isomorphic to O4, okay? Just the orthogonal group, okay? And so we're going to be working with vectors of O4, okay? They're going to be 4-dimensional vectors, and everything we're going to do is going to be organized this way. Basically, what that means is, there are, in the formulation we're going to have today, or in my lectures, there's basically one operator that we're neglecting that breaks this O4 symmetry. Again, it just is going to make life easier to work with the more symmetric version of the standard model, okay? But all the lessons we're going to learn are independent of this assumption, okay? But it's just a technical thing that as you'll see, it's gonna make life a bit easier, okay? So with that in mind, let's actually try to write down these EFTs. Oh, yes, please. Yeah. Yeah. No, I mean, in terms of the Lagrangian that I'm about to write for SMEFT, basically there is one additional operator that if we work with SU2 cross U1, we can write, but it violates the O4, okay? So as you say, we might expect the coefficient of that custodial violating operator to be suppressed by spurions, as you say, but in fact, you could choose to incorporate that into your power counting or not. Again, that's a part of the UV hypothesis, okay? But if I were doing something more phenomenological, I would just write that operator, okay? Here, because I'm really trying to give you a little bit more of a big picture perspective on what we're assuming when we formulate the theory these two different ways, I just want to keep it as simple as possible. Okay, so that's really all. But if you were doing this in the real world, you would just include a couple more operators. Okay. Yeah, but again, I mean, all this is going to do is just make it so I have to write less. And again, I'm not going to compute a single observable for you, really. So maybe if we're lucky, I'll write down some matrix elements. But yeah, we're not going to connect to phenomenology. If I were connecting to phenomenology, I would absolutely use the full. I would just add more operators. Okay. But it's really not going to affect anything about the message. Okay, about the big picture. If you like, this is a toy model for the standard models in EFT, but it's going to capture everything I'm interested in, okay? Everything I want to tell you. Great. So, let's start by defining SMEFT in this in this custodially symmetric theory. Okay. Okay, the time flies. Okay, so SMEFT, I'm going to allow the Higgs field, I'll call it phi, is a fundamental of this O4 symmetry. So I'm just going to write it as a vector, phi 1, phi 4. And phi, under an O4 rotation, phi just transforms to O times phi, where O is a 4x4 orthogonal matrix. Okay, so very simple transformation rule. And I can relate this fundamental, okay, so this is saying that I'm working in the fundamental representation of O4, okay? And that this field phi transforms in that representation. And so to relate this to capital H, we just need to identify, right? Because this is 4 real degrees of freedom. Okay, so we can repackage it into a complex doublet. Okay, so capital H, by making the following identification. Okay, and I'm not going to do the exercise for you, but you can check that this combination has the right transformation properties, you know, essentially set by this isomorphism, okay? So we're mostly going to be working in this description, again, because it's going to make life really easy. We're just working with a real vector, okay? And then we can write the most general Lagrangian so L SMEFT is now given by some function A of h squared times the kinetic term for the Higgs. Remember, we're just working with the scalar sector, so all our derivatives are partials. But of course, in the real standard model, you would upgrade these to covariant derivatives. Some other function B of h squared multiplied by d h squared squared. And then the potential, which we'll call V tilde, because we'll save V for the potential in HEFT. And then plus higher derivative operators, okay? Now, this way of writing SMEFT is not really expressing the power counting expansion, okay? Because we have these arbitrary functions, but if we actually wanted to define SMEFT, we need to say, okay, we're gonna work with SMEFT up to some order in the power counting, and here, the power counting is in mass dimension, okay? Sorry, let me just emphasize one thing before I write that. So with these functions A, B, and V tilde are real analytic functions at the origin H equals 0, okay? We're gonna talk a lot about this sort of analyticity properties as we develop these lectures, and so, but just keep in mind this is a part of the definition. And then power counting is in terms of mass dimension, okay? So I really don't have an EFT until I define the power counting and then use it to truncate the Lagrangian. Because this, even truncating here in derivatives, okay, which again I'm doing for simplicity and for reasons that'll become apparent later when we start talking about geometry. But here, okay, I've written some arbitrary functions of H, but these in principle can include an infinite tower of operators. And that's not an EFT. An EFT requires me to truncate, right? One of the properties of EFT is that it comes with an associated power counting error. We know fundamentally that we're not capturing every detail of the UV, right? That what we're doing is we're systematically expanding our observables, right, in power counting in some small parameter, which is a ratio of physical scales, and it's only a useful tool when we have a large separation of physical scales, okay? So just keep in mind, don't lose track, because we're gonna be talking about these A's and B's and V tildes and so on a lot, okay? Don't keep track of the fact that to actually use the EFT, I need to expand and truncate, okay? I have to have some, I have to make a decision. I'm gonna work to dimension 6. I'm gonna work to dimension 8, okay? And we're not gonna get to this for a few days or for a few lectures, but geometrically, we're gonna make this a connection with geometry, and geometrically, we should think of the interpretation here is that we have Cartesian coordinates. Okay? In particular, when we write things in terms of these phis, okay, you should just think of this as like 4 directions in Cartesian space. Okay? Yes? Yeah, exactly. There's one operator I'm neglecting.
So that's why you can think this as a Cartesian coordinate, but if you have that one, then you only have this.
Yeah, but so connecting this to the Cartesian coordinates does not care about this assumption of the O4 symmetry. So we can still parameterize everything in terms of a set of Cartesian coordinates. If you like, we can use the real components of capital H, even if we have the custodial violating operator. What's going to change is when we write HEFT, which I'm about to do, okay, then the geometry of the coset is going to be different, okay? So in this case, because we're working with O4, the geometry of the coset we're going to get when we break O4 is just going to be a sphere. But if we had the custodial breaking, it would be like this squashed sphere shape. It would be more complicated. And again, that's a part of why I'm making this assumption, is because it's going to make the geometric picture so much simpler, okay? But again, but all at the, just at the like sort of level of operational, you know, writing formulas and stuff, conceptually everything I'm going to say is the same, okay? Good. 15 minutes. Okay. Good. So come back over here. So now let's talk about HEFT. So now we have, remember, the symmetry is spontaneously broken. So we have Goldstone bosons of O4 mod O3, okay? And we're going to identify these as these pions, okay? Remember, these are the Goldstones for the Higgs, not the pions for QCD. And it's these objects that transform nonlinearly. So let's write the degrees of freedom. We have a singlet scalar, little h, but it's just a singlet, so we can stick it anywhere we want in the Lagrangian. We can have arbitrary powers of h, okay? And then we define this parameterization of the Goldstones. So we have n vector is n1. This is just the normalized field in terms of the pions. Because remember, in this exponential parameterization, you're going to get pi over v in the exponent, right? So we can just write this directly in terms of some n vector, and I'll kind of go back and forth depending on the context between n and pi. And but here you see, right? This has 4 components, but there's only 3 degrees of freedom, and there's this constraint, right? The 4th component is determined in terms of the other 3. The idea of writing it this way is then n transforms linearly. So under an O4 rotation, we have h goes to h, and we have n vector goes to O times n vector, okay? But built into it is this constraint, right? So it's this constrained field. And you can think about the n vector as a function of these pi fields as living on some 3 sphere, right? Because that's exactly what's being parametrized here, okay? A sphere of unit, a ball of unit radius. And so this is just a 4-component unit vector that has n dot n equals 1, okay? But now if we want to see, just to make the connection, because we'll use this linear versus nonlinear terminology a lot, so I want to emphasize that we can look at various of these rotations. So let's look at a rotation in the 1, 2, 1, 3, and 2, 3 planes. Okay? Those all just mix up these various components in a linear way, okay? So they act linearly in the sense they leave N4 invariant, right? If you like, they mix these into each other, but this form is unchanged. Whereas if instead I do a 1-4 rotation, okay, involve that 4th component, then infinitesimally, I get delta n1 is theta n4, delta n2 is 0, delta n3 is 0, and delta n4 is minus theta n4. That must be a typo. 1. So then the transformation of the pi fields, which don't have this constraint built in, are nonlinear. Okay, so just to emphasize, the transformation of the pi fields looks like delta pi 1, theta square root v squared minus pi dot pi, delta pi 2 and 3 is 0. And so here you see the nonlinear, right, behavior, right? When I do the, Anyway, I'm being kind of quick here. I just want to, this isn't so important. This just emphasizes the terminology, okay, this linear versus nonlinear way of writing the fields. Okay, so these pi's are nonlinear. I can either express the theory in terms of a constrained field with 4 components, or in terms of an unconstrained field, pi with 3 components, but with a nonlinear transformation. Okay, so there's no free lunch. I either pay the price in having that square root inside my definition of the field, or I pay the price in my transformation rule. The physics isn't going to care. Okay, so I can use either parameterization. But this is the nonlinear. Okay. So then I can write, maybe I have the space there, I can write L, the Lagrangian for HEFT now, following the same spirit as what I wrote for SMEFT. So I have 1/2 k of little h squared dh squared plus 1/2 v f of h squared dn squared, and then minus v of h plus o d4. Okay, so here I have v, not v tilde, okay, and you'll see because we're going to map back and forth. These functions k, f, and v are real analytic about h equals 0, okay? And you can think of HEFT like polar coordinates. Okay. So we have 2 descriptions, in principle of exactly the same physics, one in terms of Cartesian coordinates, one in terms of polar coordinates. Okay. And in fact, thinking about them as Cartesian versus polar is going to be very useful for us. Okay. Because again, we're going to, for reasons I have not at all explained to you or motivated, okay, we're going to want to think about things geometrically in field space, but we'll get there, okay? I'm going to spend a lot of time trying to explain why, what that means and why that's useful for the questions we're asking here. Okay, good. So remember a couple of things, okay? I've emphasized it now many times. You know, SMEFT is defined with the VEV equal to 0. And so SMEFT is an expansion around what I'll call the origin in field space, okay, where the field is 0. Compared to HEFT, where we take the VEV to be non-zero, HEFT is an expansion around the physical vacuum, okay? That's where we live. And in particular, I've said it already, but I really think it's worth emphasizing that we can start with SMEFT, but ultimately, we take SMEFT and we find the VEV, we minimize the potential, and we work with HEFT when we make predictions at the end of the day, okay? So everything, you know, the physical theory is really HEFT, but the question is, as theorists, as we're conceiving of trying to construct an EFT for BSM, to try to understand where the new physics is hiding, should we first construct SMEFT and then turn it into HEFT, or should we work with HEFT directly, okay? So again, it's the first lecture I really want to emphasize. That's the big question here. But ultimately, HEFT is the formulation of physics in the physical vacuum. Okay. Okay. So in 5 minutes, maybe I can make one more point. So this is really crucial because I keep saying things that I think are maybe confusing if you've never thought about this. Right? What I just said, it's like, well, okay, we could construct SMEFT, but then we turn it into HEFT to make calculations. Why not just work with HEFT directly? What am I doing here? What are we really talking about? Well, the point is easy to see. If we compare the expansion of the potentials, okay? So we're gonna do V tilde up to dimension 6 versus V up to 6 fields. And notice, again, I'm being a bit pedantic here, but that's because the power counting for SMEFT, which has V tilde, is in mass dimension. HEFT has this other power counting, okay? So here I'm just gonna talk about the number of fields. I'm gonna be a bit more agnostic about the power counting. So we can write the most general possible forms these can take. I'm gonna just get these on the board. Okay, so that's the dimension 6 potential. Here's the Higgs potential up to 3 fields. Okay, so it's not completely apples to apples because, again, the power counting is different, but this seems like a very natural point of comparison, okay? And notice, already in SMEFT versus in HEFT, right? Here, I have 3 free parameters organized in the way that looks, I think, probably very natural to you, right? These are the standard model plus a higher dimension operator. Here, I'm parameterizing the most general possible potential for a singlet scalar, okay? And I've got a lot more parameters, okay? So the lesson here is that HEFT is a lot bigger than SMEFT, where the standard model is some point, okay? So again, this is very sketchy. This is just the parameter space here. The standard model is a point in this parameter space. Then I start adding higher dimension operators. If I do it in a way, if I follow this SMEFT rulebook that I've been trying to outline for you this morning, then I live here. All of that is contained within HEFT because, as I just said, to do calculations, we go from SMEFT to HEFT, okay? So ultimately, we gotta work in the physical vacuum to make predictions. So of course, SMEFT has to be a subset of HEFT. But the point is that it's a subset, okay? And I think, again, this is a nice, simple example that kind of articulates that. Up to these subtleties in power counting, I don't want to lie to you, okay? So this comparison is again, it's all a bit sketchy, but intuitively, we know we're not powerful enough to work at dimension 10 with, these huge strings of fields and so on. So we're always gonna be kind of looking at low number of fields, low dimension operators. What are the leading effects, okay? And already at sort of the order, at this pretty low order, we see that HEFT is a lot bigger. Okay, so HEFT is this much bigger parameterization. And having more parameters, well, it's only helpful if you're parameterizing something important, okay? So if you get into this game and you start looking at what the LHC experimentalists are really doing, you try to actually design searches for indirect new physics, you'll quickly realize that it's hard, okay? There's a lot of operators, there's a lot of subtleties in doing the calculations. To do everything self-consistently in a way that will keep people from shouting at you about it is very tricky, okay? And people argue about this endlessly. How do we interpret these things? How do we do these fits with these huge parameter spaces? What do they mean, okay? That's all in the context of SMEFT. If now you tell me I need to work in a bigger parameterization with extra parameters, there's a huge cost. Not to mention that the power counting is tricky, okay? So if we have to, we're here to do science, right? We don't get to pick. If there's a good reason to use HEFT, then we'll do it, okay? We'll figure it out. But we should ask the question before we just dive in, right? What are we really learning by working in this bigger parameterization, okay? And that's really the, that's what I hope to communicate to you today, at least in the perturbative theories where we have control, is I want to tell you, what lives in this area where only HEFT is allowed, okay? Where we can't describe the new physics as an expansion, as a SMEFT expansion, okay? That's going to be, that's the goal. The goal is to just get at that one seemingly very simple question, which there had been, which I think we, at least in perturbation theory, building on work of Rodrigo and his collaborators have definitively answered. And the fun thing is that, as you'll see, for reasons I'm not explaining yet, in order to ask this question, is SMEFT enough? We need to, we're going to need to introduce all kinds of extra bells and whistles and formalism. Okay, in particular, we're going to have to go to these ideas of geometry of field space in order to kind of rigorously make this comparison. Okay, good. So I think I'll stop there for the first lecture. We pick back up after coffee. Thanks a lot for the questions, and yeah, looking forward to the rest of the week.